Hey guys, in this video we continue our study of electrochemistry and we're talking about galvanic or also called voltaic cells. So in a galvanic cell, it's a device where chemical energy is converted into electrical energy, and the way we do that is we take two half reactions for a redox reaction, put them in separate what are called cells. Think of them as beakers, right? And what we do is we connect those two cells together with a wire, and we use what are called electrodes that we place in the solution. So this rectangle here and this rectangle here will be electrodes. Electrodes, usually what we do is we try to make that electrode of the same material as is involved in that half reaction. So in this case, this electrode would probably be iron metal. But over here it ends up that manganese the properties of manganese are such that we can't really make an electrode out of it. So in that case, if that's the situation, what we do is we use some inert material, some material that's not going to react with anything, but that will conduct electricity well. Typically we use platinum. And so, for example here, this electrochemical cell consisting of these two half cells, they're called. Each beaker would be a half cell where a half reaction is isolated and is occurring. So what happens is the reduction half reaction ends up being the permanganate cell, half cell, and the oxidation half reaction ends up being the iron 2 cell, this over here. And so what happens is it ends up that permanganate has this attraction for electrons, stronger so than the iron 2 ion. So what it does is it's pulling on electrons here, and as it does, the net result is that an electron is pulled away from each iron 2 ion through the electrode, up through the wire, and back down over to the permanganate. It's reduced to the manganese 2 ion. The thing is though, okay, so first of all, there's a half reactions, overall reaction, we can add these up and we get our overall reaction. The electrons cancel. But this setup right here is not very useful, guys, because it ends up that as these electrons are pulled through the wire by the permanganate, we get this buildup of negative charge. So electrons are being pulled through here, and negative charge ends up building up over here in this half reaction. And also, likewise, because we're pulling electrons away from this half cell, positive charge is building up over here. Really quickly, there's enough positive charge built up here and enough negative charge built up here to oppose the flow of electrons through this wire. The negative charge is repelling like charges, so pushing back, and the positive charge that built up here is pulling the opposite charge, pulling the electrons back, and the flow of electricity stops real quickly. But we have a workaround. We use what's called either a salt bridge or a porous plug. Basically a salt bridge, let's look at the salt bridge first. They're basically the same thing. So in the salt bridge, what we have is we have this tube that we can put one end into each beaker that contains the half reaction, the half cell. And we have a porous plug in the end here of each end of the tube. And in here we have a solution that contains an ionic compound in water, and that ionic compound is one whose cation and anion will not interfere with any reactions that are going on out here. So see what happens is as the electrons flow through this wire into this electrode and the negative charge builds up over here in this half cell, that negative charge pulls the positively charged cation into this cell. And that positive charge balances the negative charge that's building up. Likewise, the positive charge that's building up over here, where oxidation is happening, pulls the negatively charged anion, say chloride, over this way, and the negative charge on the anion, the chloride, balances the positive charge that's built up here. So we get no net buildup of electric charge, and this reaction, this flow of electrons can proceed. Porous plug works basically the same way, only it eliminates the tube in the middle. It's just, if you have a setup where all you have to, where you can connect the two half cells in this sort of manner, then all you have to do is basically put a porous plug there and it'll work. All right, so cathodes and anodes. The electrode where oxidation occurs is called the anode. The electrode where reduction occurs is called the cathode. Okay, This is one place, guys, this is a heads up. This is one place where it gets really easy to be confused if you mix these two up. The way I remember, whatever it takes, there's all kinds of mnemonics out there that you can look up that might help you. The way I remember it is this. I remember that anode and oxidation both start with a vowel, A and O, where reduction and cathode both start with a consonant, R and C. So cathode, reduction, both consonants, anode, oxidation, both vowels. Whatever works, right? So in this setup right here, if electrons are flowing this way in this electrochemical cell, oxidation is occurring here, which means it's the reducing agent, right? Just the reverse. Reduction is happening over here where the electrons are flowing into, and that's the oxidation, oxidizing agent rather, on that side. So the anode where oxidation is happening is over here. The cathode where reduction is happening is over here. Cell potential. So as we described a minute ago, in a galvanic cell, the oxidizing agent, the thing that's being reduced, in one cell, you can think about it kind of as pulling the electrons through a wire from the reducing agent, the thing that's being oxidized, in the other half cell. The strength of that pull is called the cell potential, E cell, or electromotive force, EMF, of that cell. The unit of cell potential is the volt, capital V, defined as the amount of work in joules per amount of charge transferred in coulombs. Remember, coulombs is the unit of electric charge, work or energy. We use joules. So 1 volt is equal to 1 joule per coulomb. This is a nice little relationship to have in your mind, guys, particularly when we get to the next section of this material on electrolysis. All right, so how do we measure the cell potential? Well, we can use something called a voltmeter, and basically we hook this cell, each half cell up, to these wires, and these wires run through the voltmeter, which measures the voltage between these two cells. And a small complication, which we can deal with, but it's sort of inconvenient, is that every time we hook this voltmeter up to this electrochemical cell, there is some resistance in this circuit. These wires and these electrodes themselves have some resistance to that flow of electrons. And it's different for each set of wires and electrodes. And so we can take that into account, but we have to sort of calibrate that voltmeter for that particular setup each time we use it. Which, it's inconvenient, but we can do it. If on the other hand we use something called a potentiometer, what the potentiometer is basically, it has an external power supply, and what it does is it supplies a current that resists the current of the electrochemical cell, and it measures its own current, and it knows exactly when it's just balanced the current due to the electrochemical cell, and so now it knows that the current that it's pushing back with is exactly equal to in magnitude but opposite in sign to the potential of the cell. And there's no, the resistance is taken out of the equation here. And so that measures it directly without worrying about the calibration. That's nice and handy. We can just we still have to calibrate it, but it's nice. All right, so standard reduction potentials. So you can look up, there are tables and tables, guys, of what are called standard reduction potentials. And a table of standard reduction potential lists the voltage, the potential for hundreds, they have hundreds and hundreds of half reactions of half cells. They're all listed as reductions, right? So electrons are on their left, right? And the way that we got these lists, these tables of standard reduction potentials is, thing is, we can't measure the potential of 1/2 of an electrochemical cell, of just 1/2 cell. We need something to, either pull electrons or donate electrons to it. So what we do is we define a standard. It's sort of arbitrary. And that standard is called the standard hydrogen electrode, or SHE. And under standard conditions, which remember, standard conditions for a gas, the standard hydrogen electrode has hydrogen gas in it. So the pressure of that hydrogen gas is 1 atmosphere, standard conditions. And it also has hydrogen ion in it, so the concentration of the hydrogen ion is 1 molar. So we define the potential of that SHE as being exactly 0 volts. So now you see what we can do is we can make that, the standard hydrogen electrode, one half cell in an electrochemical cell. And we put another half cell on the other side. Let's say the zinc electrode, zinc half cell. And we measure with our voltmeter the potential of this whole cell. Let's say we got, positive 0.76 volts. That potential that we measure, it's the sum of the potential of the cathode, where reduction is happening, and the anode, where oxidation is happening. Well, if the cathode is the standard hydrogen electrode, and we define that as 0, that means that we now have the potential for the other half cell, say the zinc. So if the cathode where reduction is happening is 0 volts, and we measure a positive 0.76 volts, that means that for zinc being oxidized, that potential is positive 0.76 volts. Now see what that means, and this superscript 0 means standard conditions. It means if we looked up in a table of standard reduction potentials, which are all based on the standard hydrogen electrode, we would see the reduction potential for zinc as being negative 0.76 volts. The same magnitude but opposite sign, because see, this is an oxidation, right? And the reduction is the same magnitude but opposite sign. So now that we know what zinc's potential is, we can connect that to a different half cell, let's say copper 2 sulfate in solution with the copper electrode, and measure the potential of that cell with our voltmeter. When we do that, let's say we get positive 1.10 volts. Well, we know that the potential we measure is equal to the potential of the cathode plus the potential of the anode. And so if we know zinc's anode potential is positive 0.76 volts, it's real easy to solve for this, and we get a positive 0.34 volts. If we got a negative number here, that would just mean that the copper is actually being reduced and zinc's being oxidized. All right, so what's going on here is we put our voltmeter in the circuit. The electrons flow from the zinc to the copper, and at the zinc electrode, so it's zinc metal is pretty easy to find, so we can make our electrode out of zinc here, and copper, same thing. So we'd have a copper electrode over here because the copper 2 ion is what's in solution in this half cell, zinc 2 in this half cell. And so as the copper 2 pulls electrons through this electrode, through this wire, through the voltmeter, they're being pulled away in this blow up down here from the zinc ions, leaving behind zinc 2 ions, right? Positive charge starting to build up. But we have our porous plug, so we don't care. And then electrons go here and reduce the copper 2 ions. So the electrons flow out of the electrode, which is this picture right here, onto the copper 2 ions, reducing the copper 2 and building up negative charge over here. But again, our porous plug takes care of that problem. All right, so how do we combine half reactions? This is real similar to what we saw when we were balancing redox reactions. But one thing that's really important to get out of this here, guys, so pay attention to this, is that remember, when we look up in our table of standard reduction potentials, everything's written as a reduction, right? Electrons on the left, and it gives the potential for that reduction. So what you do is you look up the half reactions for each of your half cells, and you compare them. Whichever has the least positive or more negative standard reduction potential is the one that's actually going to be oxidized. And so what we do is we just flip that equation, change the sign of the potential for that cell. Once we do that, then just like we do with redox reactions, we get the same number of electrons. We multiply through by some integer to get the least common multiple of the numbers of electrons, add the two resulting reactions, get the balanced equation, and when we add those, we add the potentials, cell potentials, and that gets us the potentials for the half cells, and that gets us our overall cell potential. Now, one thing to look out for, guys, when we multiply through by some number to get the least common multiple of the numbers of electrons, we do not do that to the potential for that half reaction. We leave that alone. The only thing we do to the potentials is we reverse the sign of them if we flip an equation. That's the only thing we do. We do not multiply. So why don't you guys give that a shot? See if you can follow that procedure and write the balanced equation and find the overall cell potential for the reaction that results when we combine these two half reactions. Give it a shot and come back when you get your answer. Welcome back, guys. So first thing we're going to do is we're going to compare these two. We see that this one in white, the perchlorate half reaction, has a less positive, a lower cell standard reduction potential. So that's the one that's going to be oxidized. So we flip it. We put the chlorate on the left, the perchlorate on the right, and so on. And we change the sign of the potential for that half reaction. Now we have to get the numbers of electrons the same. The least common multiple of 2 and 5 is 10. So we multiply this one through here, the oxidation half reaction by 5, the reduction half reaction by 2, just like we did when we balanced redox reactions. And we get this down here. Now notice, okay, we did not touch our potentials for our half reactions when we multiplied through. They stay the same. And now we add the equations as well as the potentials. So just like we did balancing redox reactions, these 5 waters on the left cancel 5 of these on the right, and we leave 3. The electrons, of course, cancel. These 10 hydrogen ions cancel 10 of these hydrogen ions, leaving 6. And so we get our balanced equation. And our cell potential is just the sum of these two. Notice we've changed this sign because we flipped this one, and then we just add them. So E cell equals E cathode plus E anode. Remember that. All right. Line notation. Line notation is just a shorthand that we have for describing an electrochemical cell. It's a very useful shorthand. So when we're writing an electrochemical cell with line notation, okay, so this is how to do it. Remember, the anode is on the left and the cathode is on the right. And so what we do, and you'll see this in a minute, well, I'm going to let you try it. We write the symbol for the anode on the left, okay, and it's going to be a solid. So for example, in this one right here, which you're going to do in a minute, anode is where oxidation is happening. So because electrons are flowing this way, the iron is being oxidized to iron 2. And so this anode would be made of iron metal. So we'd write FeS for the solid, right, on the left. Cathode, this case it's platinum because we cannot make a piece of metal out of manganese very easily. So we use an inert electrode, and you're told it's platinum. So there's other ones you could use, but in this case we're using platinum. That's going to be on the right. So we have the left iron, Fe solid. On the left, on the left, Fe solid. On the very far right, Pt solid. And then this porous plug or salt bridge we represent with a double line that separates the two half cells. And then within each of these two half cells, we write everything that's in that solution that's relevant to the reaction. We don't write water or anything like that usually. But anytime there's a phase boundary, we use a single line. For example, like the anode on the left, the Fe, is a solid, so we put Fe, solid, single line, and then in this case we put what's in here, double line to represent the porous plug, and then everything that's in here, and then a single line, and then Pt for solid. So that's what this is saying down here. The species that are present in each of the half cells are shown between the electrode for that half cell and the double line. So see, that's enough for you guys to figure out how to use line notation to describe this cell. Just give it your best shot and come back when you get your answer. Welcome back, guys. So here's what it looks like. So we have the anode on the left, and the electrode is made up of iron. So we put Fe solid, single line to represent a phase boundary between the solid and the liquid. And then in this solution, the only thing that's relevant to the electrochemical reaction is the iron 2 ion. So we put Fe2+. These are all 1 mole because we're under standard conditions here. Then we have a double line representing the porous plug. And then everything that's in the solution in the cathode, where reduction is happening, permanganate ion, manganese 2. Actually, this is wrong charge. But there we go. Manganese 2 is right. And we have hydrogen ion also. And then finally we have a single line to represent the phase boundary, and we have platinum. So that's line notation, very handy. So this right here, is pretty much describes this electrochemical cell. The only thing that it doesn't have in it is the cell potential, which we can get from the standard reduction potentials. So here's another example. Given these two reduction half reactions, standard reduction half reactions and their potentials, standard reduction potentials, we want to write the balanced electrochemical equation. We just saw how to do that. Write the line notation that describes the electrochemical cell that's comprised of these two. So again, these are all both reduction potentials, and you can look them up in tables. There's tables and tables and tables. And so remember, so this is something that people tend to get tripped up at first. So I want to really emphasize it. In a table of standard reduction potentials, they're always written as reductions. So one half reaction is going to be the oxidation half reaction, right? Remember, we have to figure out which one that is. And that's going to be the one whose standard reduction potential is least positive or most negative. And whichever one that is, the one that's going to be the oxidation half reaction, well, we take that reduction half reaction, we flip it, and we change the sign of the standard reduction potential. Right? Now it's an oxidation potential. In that case, the iron is going to be flipped. And remember, a galvanic cell, that's an electrochemical cell that runs spontaneously, which means that the cell potential for a galvanic cell will be positive, always. So why don't you guys see if you can get the cell potential, the balanced electrochemical equation, and line notation for this electrochemical cell. Come on back when you get your answer. Welcome back, guys. So we flip the iron. We change the sign of its potential, so now it becomes positive 0.44 volts, right? Because negative 0.44 is more negative or less positive than 1.51 positive. So now that tells us that the iron is where oxidation is happening, so that's the anode. That's going to be in the left, by the way, in our line notation. And the permanganate, that's where reduction is happening, that's the cathode. Anode, oxidation, cathode, reduction. Again, in this case, because we can't make an electrode very easily out of manganese, we're going to use an inert metal like platinum. So the cell potential is just the standard cell potential is what we're doing here. The standard potential for the cathode plus that of the anode, which now is going to be plus 0.44 and positive 1.51. So we get a positive 1.95 volts for this cell potential. Balanced equation, so like we did, least common multiple is 5, multiply, add up, and we get this equation right here. And check that, make sure we get the same answer, guys. And so our line notation is going to have the anode, where oxidation is happening on the left. Its electrode will be iron. Again, typically, if we can, the same metal as is involved in the half reaction. Single line to represent a phase boundary. The iron 2 ion is in solution. A double line to represent the salt bridge or porous plug. Everything that's in solution on the right. Permanganate, manganese 2. So permanganate, manganese 2. So these are the things that are in the reduction half reaction that go down here. Permanganate, again, I did this here. This is just one negative charge. The manganese 2, which is right here. The hydrogen ion, right here. We don't write the waters, right? And the electrode, we're going to use platinum. This is pretty common. If we can't make an electrode out of that material, we use platinum. There we go. So this is a good description for this electrochemical cell, which we're going to see right now. What's a complete description of a galvanic cell or voltaic cell? Well, it has to, when you're asked, guys, for the complete description of an electrochemical cell, it's going to have all these parts. Somewhere in it, it's going to have this overall cell potential and the balanced cell reaction. The direction of electron flow for a positive cell potential must be indicated. Have to label the cathode and the anode, and you have to say what each electrode is made up of, right? Platinum or whatever, as well as describing which ions are in each of the half cells. So for example, let's see if you guys can apply this to this galvanic cell that's composed of these two half reactions. These are both, as you commonly find, written as reductions. So go ahead, see if you can do that, and come on back when you get your answer, guys. Welcome back. So first, the cell potential and the balanced cell equation. When we look at these two, we actually, let's go back over here. We see that of these two potentials, the one for the iron 3 being reduced is less positive than for the silver being reduced. So less positive means it's flipped, becomes the oxidation half reaction. So we flip the iron half reaction, change the sign of the cell potential, negative 0.77 volts. In this case, the electrons are already the same, 1 and 1, so we don't have to really worry about multiplying. We add these up, we get the cell potential, 0.80 plus negative 0.77 volts is 0.03 volts. The overall equation is going to look like this. Right here. Oops, do this. And there's our overall equation, complete equation. The direction of the electron flow for a positive E cell is going to be shown right here. This is number 2. So number 1, there's the cell potential. So over here, this is our complete description. Cell potential, direction of electron flow, the E minus and the arrows. 3, labels for the cathode and the anode. Anode is where oxidation is happening. That's right here. This is number 3. And cathode is where reduction is happening. Silver is over here. And the makeup of each electrode and the ions in each compartment. So PT here shows this is platinum. Could have used iron, but in this case we just chose to use platinum. This we chose to use silver, same as the material in here. We could have used platinum in both cases. It gets kind of expensive, but because platinum is actually pretty expensive. And in here we have the silver ion. So in here we have iron 2 and iron 3. So iron 2 and iron 3, silver ion over here. And that's all there is to that, guys.